Hello and welcome to this presentation about a DeltaState JSON conflict-free replicated data type. Collaborative applications enable users to concurrently work on the same document. Cloud-based data synchronization solutions are typically used to support these applications. When a document is concurrently modified by different users, changes made to each replica are propagated on the network in order to update other replicas. Updates can be propagated either in real time, the so-called synchronous collaboration, or asynchronously, to implement an offline-first solution. As data is managed by a third party in the cloud, concerns about security, privacy, and data portability arise. These issues can be partially mitigated by the Solid project, which aims at decoupling data storage from services in order to redecentralize the web. Pods, or decentralized data stores, allow for storing personal data while retaining full control. Recognizing the benefits of such an approach, we propose to use pods in order to support the implementation of collaborative applications. Moreover, we want our solution to work on practically any kind of storage and sharing solution, such as share folders, databases, emails, thumb drives, and so on. Our goal is to support asynchronous collaborative editing of complex data, namely a JSON document. To prevent conflicts without relying on a central server or explicit consensus protocols, we implement a conflict-free replicated data type, or CRDT. Our solution implements a DeltaState CRDT, which does not require explicit editing of the data structure in order to record the modifications. An application can retain its existing data model, and only JSON serialization and deserialization procedures must be implemented. Our data structure is essentially an append-only collection of JSON objects. Each object has a unique identifier. A reversible data transformation algorithm allows for destructuring an arbitrary JSON document into a collection of objects. Objects can be modified during their lifetime. Each modification produces a new version or revision. Each revision is assigned a revision string, which includes a monotonically increasing numerical index and the hash value of the contents of that version of the object. The history of an object can be represented as a sequence of revision strings. The combined sequences from all replicas result in a revision tree. A deterministic algorithm is used to choose the current version of an object. On each replica, the set of all trees is the revision information of our data structure. The data corresponding to each revision is stored into a map, where the key of each object is the hash value of its content. The state of each replica comprises both the revision trees and the object map. When the data structure is updated, we keep track of the changes made to the revision tree and the data map. We call this a delta update. Several delta updates can be grouped together. We call this a delta state. Delta states are uniquely identified and are propagated on a network or stored on a shared location to allow other replicas to update their local state. Delta states can be simply saved on a shared storage. Merging delta states is a commutative, associative, and idempotent operation. At any moment, the state of the data structure can be decomposed into delta state.